All right, y'all. So here is the Chapter 7 exam style questions. And with that said, let's just jump right into it. So consider the following reaction in which phosphorus pentachloride, PCl5, decomposes to form phosphorus trichloride, PCl3, and chlorine gas, Cl2. The value of Kc is 1.2 times 10 to the negative second at 500 Kelvin. I apologize, as I put this on my iPad, formatting gets a little mixed up. So with that said, before I even start the question, I just want to notice a couple things right off the bat. I notice that my equilibrium constant is actually less than 1. Big thing. Kc is less than 1. Therefore, this reaction is going to be weighted towards the weighted towards the reactants. It's going to want to go back towards PCl5. That's kind of where we're going to have more. Another thing to notice right off the bat is when I look at this, my enthalpy is negative. This is an exothermic. You may want to start noticing these things before you even start doing the questions because likely these will all come up later in the question. So we can just start with A, deduce the equilibrium constant expression. We can do that. The equilibrium constant is going to be the concentration of the products, PCl3, to the power of their coefficients, Cl2, all over PCl5. Now, you'll notice that I am missing our exponents, but in truth, I am not. This is a balanced equation as is, 1, 1, and 1. Therefore, I don't need exponents. The equilibrium constant is right there. All right. State the change in equilibrium position when the temperature of the reaction is decreased. Well, this is perfect. We already know that when the reaction progresses forward, we release energy, which is exothermic. And that's really important. That's what we have right here. We have an exothermic reaction, and we're saying when we move forward, it's going to be exothermic. So when we decrease the temperature, when temperature decreases, this equation will want to add temperature. So now we need to add temperature. And we know that when an equation is exothermic, it's going to release energy. That energy is in the form of heat. So we know this reaction is forward. So our answer is this is forward. And you get the marks honestly just saying forward, but you should note that it is exothermic because it says state, that's 1 mark, explain, that's your 2nd mark. So forward and release energy, exothermic, 2 marks. All right, let's now go to the 3rd part. Using your answer to part B, state the effect, if any, on the value of the equilibrium constant Kc for this reaction. So this one, we can just kind of do a little mental math. If we know that the reaction shifts forward, then we know that we are going to be making more product divided by less reactant. Therefore, Kc increases. Basically, all I'm saying is that if we go back to our equation up here, if we are making more of the PCl3 and more of the Cl2, and we're making less of the PCl5, the number on top gets bigger, the number on the bottom gets smaller, and therefore Kc increases. So you get 1 point for mentioning, honestly, all of that. You should mention that the reaction will increase, or the Kc will increase because of the forward shift. All right, moving on to part D, the difference between reaction quotient and equilibrium constant. Now, This is just kind of difference of where we are in the reaction. So I can say something like the equations are the same, but Q is measured at non-equilibrium times in the reaction. Kc is equilibrium. So when you are doing this, you need to remember that the reaction quotient only happens when it's not at equilibrium. The equilibrium uses the equilibrium constant. Got to remember that. All right. So part E, 0.1 mole of PCl5, 0.250 mole PCl3, and 0.250 mole Cl2 were mixed in a 1 decimeter cubed flask at 500 Kelvin. Predict the direction of our reaction. Show you're working. So the first thing we want to know is that these are being mixed, which tells us we are at non-equilibrium. Another word we learned for this is dynamic equilibrium, as it's shifting towards equilibrium. But because we're not at equilibrium, we are measuring Q. Q tells us that it's pretty much the exact same thing. This is going to be 0.250 mole over 1 decimeter. I'm just going to shorten this all out. This is 2.50 molar times 0.250 molar, all divided by 0.100 molar. Because once again, I am using the same equation from right here. So I'm going to actually just skip ahead because I already have this math down, and our reaction quotient is going to be equal to 0.625. Now, here's the important thing. We learned that when our reaction quotient, when our Q is greater than our Kc, which means we have more products than we do, we have more products than we do reactants at equilibrium. We know that we are going to shift back towards the equilibrium. So if Q is greater than Kc, and just a reminder, Kc was mentioned at the top as 1.2 times 10 to the negative second, or 0.012, then we know that this reaction will shift left. Real quick, I'm just going to come over here to the side and explain that last part one more time. We know that the top part over the bottom part for Kc, this is some amount and this is some amount. If this top part gets bigger and this bottom part gets smaller, this whole thing will try and equilibrize or equilibrize, whatever. It'll try and come back to equilibrium. So it will do whatever it can to make the top part smaller and the bottom part bigger. It's going to always try and do the reverse of what's happening. It wants that balance. We notice that we got a larger number over here. Because we got a larger number, we know that the top right now is bigger than the bottom for what would normally be happening at equilibrium. Therefore, we need to get rid of whatever's at the top and add to whatever's at the bottom. This is like math theory. This isn't even chemistry. This is just the ideas of math. To do this, now we bring in the chemistry, the reaction will shift towards the reactants. It will increase the number on the bottom and therefore decrease the number at the top, making the whole thing smaller to match Kc. Okay. Last one. Explain the effect of a catalyst on the equilibrium position of a reaction. And this one is just kind of, you got to think about it or memorize it. But either way, there is no effect. Remember, equilibrium is where forward rate is equal to reverse rate. But a catalyst affects both equally. So it'll make the forward rate faster and it'll make the backwards rate faster, which at the same time means that there is no change whatsoever because all it's doing is providing a different pathway. If you want to throw that in, just you can always add catalyst provides an alternate pathway. It's always a good thing to add in. All right, that is question 1. Question 2. The following equilibrium is established at 1700 degrees Celsius. CO2 gas plus H2 gas reacts to form H2O plus CO. And these are all gases. Something to note right off the bat is that this is already balanced, so we don't have to balance anything. Now, if only carbon dioxide gas, so let's go ahead and look at these. If only carbon dioxide gas and hydrogen gas are present initially, sketch on a graph a line representing the rate against time for the forward reaction and the reverse reaction shortly after equilibrium is established. All right, so we kind of have to think about this. If we're only starting with reactants, that means right at the top, our rate for the forward reaction is going to be high. And then it's going to slow down. Then it's going to slow down over time. Because as we decrease in reactants, the rate is going to slow down. That's just what we learned in chapter 6. As the concentration of reactants decreases, the rate decreases. So let's go ahead and do time and rate. So we start with a high rate and eventually come down to a kind of low rate. I want to redraw that a little better. Eventually the rate's going to level out. We know the rate's going to level out. Oh, sorry, one more time. I'm just not happy with this. There we go. So the rate's going to start fast and then go slow and level out. This is our forward. You'll notice the rate doesn't go to 0. So the rate is not equal to 0. The reason for that being is we know at equilibrium, the forward reaction still occurs. It just occurs at the same rate as the backwards reaction. But we know that the rate levels out completely. The rate does level out because we're at equilibrium, which means that the concentrations remain the same. And if concentration of a reactant remains the same, the rate of the reaction also remains the same. For the reverse reaction, I'm actually going to put it on the same graph. And we'll notice that it is an exact mirror of this. You'll also notice that the rate does not equal 0 here, but it does equal 0 here. This is a 0 rate. And the reason this is a 0 rate is because when the reaction starts, there is no product. Therefore, there can be no reverse reaction. If we don't have product, how can we do a reverse reaction? So it's very essential that these start on opposite ends and then they come together because the rates are equal, which is what we describe as equilibrium. So to kind of sum this all up, for the forward reaction, we have a high concentration, therefore high rate. As the reaction proceeds, rate decreases and levels at equilibrium. For the reverse reaction, it's the opposite. No concentration. zero rate initially. As reaction proceeds, concentration increases and rate does as well. And then just a last little cherry on top. At equilibrium, rates are equal. That way you fully explain that you know everything. And you get all 7 marks. You get 7 marks for this question. So just make sure you really, really, really fully explain everything that's going on. All right. B. Kc for the equilibrium reaction is determined at 2 different temperatures. At 850, Kc is 1.1, whereas at 1700, Kc is 4.9. So, on the basis of these Kc values, explain whether the reaction is exothermic or endothermic. So, we know that Kc increases when temperature increases. That means when we add temperature or add heat, we make more products. Because we're making more products, we know that making more products is using the heat. And we know that because our equation is trying to consume energy to balance the temperature change. Whoops. The temp change. Therefore, if it's consuming energy, we know this is endothermic. And so you get marks for that. You get, say it's endothermic, say it increases with temperature and the forward reaction heat is used up or consumed. And there you go. That is all the points for question 2. Moving on to question 3. For the reversible reaction, H2 plus I2 creates 2HI, already balanced. And we know that delta H is above 0. Therefore, it is going to be endothermic. We're not given a value. We just know it is above 0. And our Kc is 60 at some given temperature. All right, that means that we know that we are favoring our products. Give the equilibrium expression. This should be not a problem for y'all at this point. It's going to be HI, concentration, but this time we're squared because of our 2 coefficient, divided by H2 times I2, and these are all concentrations. Perfect. That'll be the easiest points of this problem. B, for this reaction, what information does the value of Kc provide about the relative concentrations of the products and reactants at equilibrium? Well, we know that when Kc is higher than 1, we have more products, more concentration of products than reactants. And you should just like have this ready to go. We already realized that just as we were reading the problem. It's, once again, those things that we notice. All right. What effect, if any, will an increase in pressure have on the equilibrium position? So we know that pressure involves gases, and we have some gases. In fact, we have 1 mole here, we have 1 mole here, and we have 2 moles here. And I get those from our coefficients. So I see that we have the same concentration of gas both on the right side and the left side. So this is going to be no effect. Whether this reaction moves forward or backwards, it does not add or reduce pressure in the system because we have the same number of moles of gas on either side of the reaction. I'm going to start using RxN. I'm tired of writing reaction. I'll just let you know right now that they did not say explain. This will not get you extra points. I'm putting it here because I want you to understand what I'm saying, not because it's going to give you any points. You only get points for saying no effect. All right, D. Explain why an increase in temperature increases the value of the equilibrium constant for the reaction above. Well, it turns out this is exactly the same as our last problem on our last problem, which is the reaction is endothermic. And so we know that not just the reaction, sorry, this is my bad. You should be more specific in equilibrium problems. You should say the forward. The forward reaction is endothermic. It will consume or use heat as temperature increases, pushing the reaction forward, pushing the reaction forward. So just make sure that you explain this one fully because this one says explain. So you will only get the points if you actually say that it will consume or use heat as the temperature increases, pushing the reaction forward, which actually I'm noticing. Oh, no, we're good. We're all good. It does tell us that it increases the equilibrium constant, which means I have not finished this answer. It will push the reaction forward. This makes more products, consumes reactants, therefore increasing Kc. So I needed to make sure that I know through the equation in Kc that I outlined up here that I am increasing the products. So increasing the products, decreasing the reactants, therefore Kc will increase. All right, last problem. Let's run right through this one. So the following equilibrium is involved in the industrial production of nitric acid from ammonia. And once again, we're given a balance equation. We notice straight from the top, delta H is negative, therefore this is going to be exothermic. Just pick those up right off the bat. Describe the effect, if any, of each of the following changes on the equilibrium concentration of nitrogen monoxide in a particular equilibrium mixture. Give a reason in each case. So this is specifically asking about the changes on the equilibrium concentration of nitrogen monoxide. That is this right here. So that's all we're looking at. We want to know what happens to this chemical. I don't care about anything else. We don't care if it's forward, back. We just want to explain in terms of nitrogen monoxide. So first thing, increasing the pressure at a constant temperature. Well, we have to check how much gas we have in each. We have 4 plus 5 moles here. We have 4 plus 6 moles here. We have 10 moles versus 9. So when we increase the pressure, we actually want to start getting rid of gas. So when we increase the pressure, we want to reduce the moles of gas. Because when we reduce the moles of gas, we will then reduce the pressure. Reduce moles of gas to reduce pressure and balance. Therefore, our actual answer, sorry, the green is just me thinking out loud, but our actual answer is that we say equilibrium shifts left. Again, we're shifting left to our reactants to the lower number. Therefore, NO, concentration of NO is reduced. Even though this is a exothermic reaction, even though we say this is exothermic, it doesn't really play an effect. I don't actually have to write that it's exothermic. I'm going to go ahead and erase it. It says at a constant temperature, and whenever you talk about temperature, I'm just like, oh, well, we should just mention right here really quick, exothermic. Sorry for that terrible writing. All right. Increasing the temperature at a constant pressure. So this one, we are increasing the temperature. If we're increasing the temperature, we want to figure out how we can kind of work with that. So we already said that this is exothermic. So as we add temperature, we want to try and reduce temperature. So here, we're going to take exactly what we said before. It's exothermic, but now let's bring that into play. If forward is exothermic, then reverse is endothermic. The reaction shifts left to use heat. Concentration of NO is reduced. And done. All right. Last thing. Addition of a heterogeneous catalyst at constant pressure and temperature. So we already know that catalysts do nothing, no effect. Because we know that, so sorry, before I get ahead of myself, I should say NO concentration does not change. Remember, we are talking about all of this in terms of NO, and I had already forgot. So we said that catalysts increase rate of forward and reverse equally. All right. So part B, deduce equilibrium constant expression Kc for the forward reaction. Well, this one we know we're just going to put the products over the reactants. So the product is the concentration of NO to the fourth because of that 4 exponent, the concentration of H2O to the 6th because of that 6 exponent, the concentration of NH3 to the 4th, and lastly, the concentration of O2 to the 5th. There we go. Easy points right there. Whenever they ask about the equilibrium constant expression, just know that's your easy points. Okay, so the last question. Identify which of the changes in part A will affect the value of Kc and predict whether the value of Kc will increase or decrease. So right off the bat, we know that temperature changes equilibrium. And when we know in this one where we have our temperature changing equilibrium, we shifted to the left. So we know that we're shifting to the left. Therefore, we're going to have more reactants. So Kc will decrease. And there you go. That's all you have to do. I hope you have a great night. And yeah.